Good afternoon. Okay, എല്ലാവരും join ആയോ? Okay. എല്ലാവരോടും join ആവാൻ പറയണം. Okay. Okay, അപ്പോൾ നിങ്ങളുടെ അറ്റൻഡൻസ് ഒന്ന് തന്നെ കേട്ടോ, ചാറ്റ് ബോക്സിലിട്ടെ. ഞാൻ കുറച്ച് കഴിഞ്ഞിട്ട് ഒന്നും കൂടെ വിളിക്കും. അപ്പോൾ ചാറ്റ് ബോക്സിൽ അറ്റൻഡൻസ്. Okay, in the previous class we discussed about different problems, okay, of which we discussed three satisfiability problem. Okay, so what is satisfiability problem? What is meant by a satisfiability problem? It is one of the hardest problem. Okay, satisfiability problem is one of the hardest problem. And we discussed what is satisfiability problem in the previous class. Okay. So next we want to discuss what is Clique problem. Okay, Clique is the next topic. Okay, so in the previous class we discussed these concepts. Now today we want to discuss what is satisfiability problem and what is Clique problem. Okay, so this is satisfiability problem. In the previous class we discussed this concept. Okay, now we are moving to the Clique problem. Okay, so Clique. Okay, Clique problem. Okay, please note this Clique problem. Okay, Clique decision problem. Okay, so what is a Clique problem? Okay, what is a Clique? First we want to define what is a Clique. Okay, what is a Clique? A Clique, okay, this is very important topic. Okay, so a Clique is a subgraph of a graph such that all the vertices in this subgraph are connected with each other. Okay, so this is the definition of a Clique problem. What is a Clique means? A Clique is a subgraph. Okay, we know what is a graph and what is a subgraph. So a Clique is a subgraph of a graph such that the condition is all the vertices in the subgraph. You can note here, all the vertices in this subgraph are all the vertices in this subgraph, okay, in the subgraph, okay, are connected with each other. Okay, so that is the subgraph in that graph should be a complete graph. Okay, it should be a complete graph. The subgraph in the graph should be complete. Okay, that is called a Clique. That is called a Clique. What is a Clique means? A Clique is a subgraph of a graph such that the condition is all the vertices in this subgraph are connected with each other. That is, that subgraph should be a complete graph. Okay, this is a Clique problem. This is a Clique. Okay, this is the definition of ClickQ. Okay, next we are moving to what is ClickQ decision problem. Okay, next we want to discuss what is a ClickQ decision problem. Okay, next we want to discuss what is a ClickQ decision problem. Okay, so I hope you can hear and the connection is okay. Okay, so what is ClickQ decision problem? We already studied what is a decision problem. That problem will give an answer yes or no. Okay, if a problem give an answer yes or no, then that problem is called a decision problem. Okay, now the ClickQ problem can be considered as a ClickQ decision problem. Okay, ClickQ decision problem. So this is the decision problem of ClickQ. The decision problem is to find a ClickQ of size k exists in the given graph or not. So this is the ClickQ decision problem. Okay. So what is the problem? What is ClickQ decision problem means? The decision problem is to find a ClickQ. I'm underlining it. Okay. Find a ClickQ of size k. Suppose I given the value for k is equal to 5. I want to find a ClickQ of size 5 in that graph. And that is the problem. Okay, so this is the ClickQ decision problem. Okay, so it will check whether such a ClickQ exists or not. That is only important. Okay, that is called a ClickQ decision problem. Okay, okay, please respond. Anaga, please respond. Anaga, okay.
Sir, okay.
Okay. So what is a ClickQ decision problem means? The decision problem means it should give an answer yes or no. Okay. So what is ClickQ decision problem? Find a ClickQ of size k. Okay. Okay. This is a decision problem. If such a ClickQ of size k exists in the graph, then it should give an answer yes, else no. So this is the ClickQ decision problem. Now the same problem, another variation of the problem. We already studied what is decision problem and what is an optimization problem. Okay. So the ClickQ optimization problem also there. So what is a ClickQ optimization problem? What is a ClickQ optimization problem? Okay. So what is a ClickQ optimization problem? The problem is to find the maximum sized ClickQ of a given graph G. Okay, that is, this is an optimization problem. Okay, I want to find the maximum or minimum of some variable. Okay, so ClickQ optimization problem is, the problem is to find the maximum sized ClickQ. There may be a lot of ClickQs, of which I want to find out the maximum sized ClickQ. That is called an optimization problem, and that is the ClickQ optimization problem. Okay, so there are two type problems: ClickQ decision problem and ClickQ optimization problem. Okay, so now I'm giving some examples. Okay, so you can note here, this is an example of ClickQ. Okay, for example, this is a graph. Okay, you can note here, this is a graph and there exists a ClickQ of size 3. You can note here, this is a graph and you can note this portion. Okay, what is this? This is a subgraph. Okay, this is the graph G. Okay, this is the full graph G and there is a subgraph exist. what is the property of that subgraph? You can note here, this subgraph is completely connected. Okay, what is the meaning of completely connected? From this I can reach here, here. From this I can reach here, here. From this I can reach here, here. That is the completeness of a graph. So there exists a subgraph of size 3. Of size 3. Okay, the number of vertices is 3. So there exists a subgraph of size 3. Okay, in this graph. So this is a Clique. This subgraph is a Clique. Why it's a Clique? Because it's a connected graph, completely connected graph. Okay, this is a completely connected subgraph. Okay, so this is a Clique of size 3, and you can note here this also. Okay, there exists another subgraph. Okay, these two are independent. You can note here, this is one Clique and this is another Clique. Okay, this is also a Clique of size 2. From here I can reach here. So this is also completely connected. So in this graph G, there exist 2 subgraphs, and these 2 subgraphs are complete subgraph. So there exist how many Cliques here? There exist 2 Cliques in this problem, and of which is the maximum sized Clique? This one. Okay, so we can consider 2 problems. One is Clique decision problem. Clique decision problem means it will check whether there exists a Clique or not. In this graph, there exist 2 Clique. Okay, there exists a Clique, so the answer will be yes. Okay, but if it is a optimization problem, then it will check what is the size of the maximum sized Clique. Okay, so in this case, which is the maximum sized Clique? This Clique. Okay, this Clique. So this is the maximum sized Clique in this graph. So if it is an optimization problem, the answer will be 3. Okay, if it is an optimization problem, the answer will be 3, and this is the subgraph. This is the Clique. If it is a decision problem, what will be the answer? Yes or no? Here the answer will be yes. Why? Because there exists at least one Clique. Okay, so that is the concept, and this is another example. Okay, there is a graph is given, and we want to check whether there exists a Clique or not. Okay, here you can note here there existed 2, not 2. There exist a lot of Cliques, of which I will show one example. This is a Clique. Why? Because from this I can reach here, I can reach here, from this here, here, from this here, here. So this is a Clique. Similarly, its size is 3. Okay. Then what about this one? Its size is 4, because from you can consider these 4. Okay, okay, this one, this one, this one, and this one. Okay, so what is the size? You can note here, if you consider these 4 vertices, then from here I can reach here, from here I can reach here, from here I can reach here. Similarly, from here I can reach here, from here, here, from here to here, 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 here. So it is a completely connected subgraph. Okay, and its size is 4. Its size is 3. So okay, so what will be the Clique optimization problem? Must no present. Masna? Anyone? Nitin Babu? Nitin Babu? Please respond, Nitin Babu.
Hello.
Nitin Babu, suppose this is an optimization problem. Suppose this is the click queue optimization problem. Then what should be the answer of that problem? If it is an optimization problem, okay, if it is a click queue optimization problem, then what should be the problem? What should be the answer? It will produce an answer 4. Okay, 4. Why 4? Because, okay, Nitin Babu, please mute it. Okay, so why 4? Because the maximum size to click queue here is of size 4. So the answer should be 4. Another click queue is there, its size is 3. Okay, we want to find the maximum size to click queue. So the answer is 4. If it is a decision problem, what should be the answer? Then yes or no. Here two or more click queues existing, so the answer should be yes or no, and in this case yes. Okay, so try to understand what is a click queue problem, what is a click queue, and what is a click queue decision problem, and what is an optimization problem. Click queue optimization problem examples we discussed. Okay, so now suppose in the university exam, sometimes you can expect this type of questions. Okay, so show that click queue problem is NP hard. Okay, this is the question. Show that this is the problem we are considering, and this is a click queue problem. We know now what is click queue problem. Okay, so show that this click queue problem is NP hard, is one of the difficult problems. I want to show it. Show that the click queue problem is NP hard. Then what should be our procedure? Okay. Okay, Raisa. Connection under. Okay. So here we want to show that the click queue problem is NP hard. Then what should be our procedure? 1. The first step, we should show that CNF satisfiability problem can be reduced to the click queue problem. Okay, so I want to show that the click queue problem is NP hard. Then first we want to show that the satisfiability problem can be reduced to the click queue problem. Then this problem, then we can say that this click queue problem is NP hard. That is, we want to prove it. We want to prove this concept. We already discussed what is CNF satisfiability problem. So if that problem can be reduced to a click queue problem, then this click queue problem is NP hard, because CNF satisfiability already a NP hard problem. If that problem can be reduced to a click queue problem, then click queue problem also will be NP hard. Okay, so this is the concept. Okay, so assume that CNF satisfiability is NP hard. Okay, already in the previous class I told CNF satisfiability is the reference problem we are taking to we are considering. It is a very difficult problem. Okay, this is always an NP hard problem. This is proved already proved it is an NP hard problem. Okay, so we will assume CNF satisfiability is NP hard. Okay. In the previous class we discussed this case. Give an example for NP hard, CNF satisfiability problem. Why CNF satisfiability is an NP hard problem? because it will take big of 2 raised to n. Okay, as n become 100, it will be 2 raised to 100. Okay, so it will be a very complex problem. Okay, so this is the reference problem. Okay, this is an NP hard problem. Okay, so now we want to show that the Clique problem is NP hard. So we should show this one. Okay, CNF satisfiability is reducible to Clique. Then we can say that the Clique problem is NP hard. Okay, so how it is possible? We can check the procedure. Now this is the concept. So what we want to do is that take an example of the CNF satisfiability problem. Okay, so this is the method. And first we want to take an example of CNF satisfiability problem. Okay, let it be I1. Okay, then what we want to do? We want to convert that example to this example to a Clique graph. This is I2. That is, we will take an example of CNF satisfiability problem and we will try to reduce or convert it to a Clique graph. If it is possible, then the Clique problem is NP hard. Okay, so this is the procedure. Okay, so we want to take an example of CNF satisfiability problem and convert that problem, that example, into a Clique graph. If it is possible, then the Clique problem is considered as NP hard. That is, we are applying the polynomial reduction, okay, reducibility concept here. We already discussed, and just moving to the reducibility concept. 1 minute. Okay, this is the concept, polynomial time reduction. We are trying to apply the polynomial time reduction. Okay. Okay. We are trying to use the reducibility concept. Okay, we are trying to okay, Anaka, connection okay le?
Sir, okay.
Okay, so we want to apply the reducibility concept. Okay, using the reducibility concept, this is alpha. Okay, we will try to prove a problem is NP hard. Okay, anyway, I'm coming back to the problem, and this is the procedure. So take an example of CNF satisfiability problem and convert, that is, try to reduce it to Clique graph. If it is possible, then we can say that the Clique problem is NP hard. Okay, so now this is an example. Okay, so consider a sample example. Okay, for example, this is a problem I am defining. Okay, so this is a CNF satisfiability problem I defined. What is the problem here? There are 3 variables, x1, x2, x3, and there is a formula f. The formula is called a Cnf formula, and it consists of 3 clauses. Already we discussed what is a Cnf formula. Okay, it consists of clauses. The clauses are contains the variables combined using the union operation. Okay, for example, C1, x1 union x2, C2, x1 complement union x2 complement, C3, x1 complement, sorry, x1 union x3. So there are three clauses. Okay, and these clauses are combined using which operation? Intersection operation. So this is the formula. Okay, so then you can note here, in this case there are three clauses, so you can consider k is equal to 3. Okay, next, what is the problem here? So here the satisfiability problem is to find out suitable values for x1, x2, x3 such that f evaluates to true. Okay, this is the satisfiability problem here. Okay, so there is a formula f. There are three variables x1, x2, x3, and the formula is created using these three variables and union intersection operation. Okay, like this. Then the problem is to find out the suitable values for x1, x2, x3 such that f evaluates to true. Okay, so that is the problem. Okay, so now I defined an example problem. Okay, now what I will do is that I will try to convert this problem into a ClickQ problem. What is a ClickQ problem? ClickQ is a graph problem. I will try to convert that problem to a graph. Okay, so that is the concept. Okay, so the conversion to ClickQ. Okay, this is a expression basically. I will use some logic and I will try to convert this expression to a graph. Okay, okay, so that is the procedure we want to apply. Okay, so the conversion to ClickQ. So what I will do is that this is the procedure. This is already a proved method. Okay, just I am explaining that method. Okay, so here you can note here how many this one, you can note here this one. Okay, this is close one. Okay, this is close one. Okay, this is close one. So these are nodes. This is one node, this is another node. Okay, there are two nodes in the close one. Okay, you can note here I am going to the close C1. C1 is, okay, you can note here C1. What is C1? X1 union x2. Okay, C1 is x1 union x2. So there are two variables in the C1. So what I will do is that I will represent that in this way. So this is close one. Okay, and two variables x1 and x2. For two variables I will create separate node. This is one node and this is another node. Okay, so I will consider close one, and in that close x1 and x2 is there. So for x1 I will create a node, and for x2 I will create a node. Okay, so you can note here, what is this one? This one, it indicates this from close one. Okay, that is just an indication. Okay, x1 1. Okay, so okay. So just an indication. For example, you can note here 1. What is meaning? it belongs to the close one. Okay. So similarly, what I will do, I will create two nodes for close 2. Cannot here, this is 2. Why it's 2? Because of this. Okay. Now if you consider close to x1 complement, x2 complement. Okay. So cannot here x1 complement, x2 complement. Okay. Simple concept. Similarly, I will create two nodes for close 3. Okay, this is close 3. This is close 3, x1 and x3. Okay, then what I will try to do is that I will try to create edges. Okay, only vertices are in the graph now. I will try to add edges. Okay, but edges should be added using these two rules. Okay, the first rule is should not connect the vertices of the same close. Okay, this is very important. The first rule 1 is should not connect the vertices of the same close. So what it's meaning, should not connect in this way. It is not possible. Okay, so it is not possible. I can't connect in this way. Okay, so try to understand that. Okay, so this is the concept. Okay, I can't connect in this way. Okay, this is wrong. Okay, next, second rule is it is possible to draw. This is rule 2. Okay, this is rule 2. Based on these two rules, I want to add edges. It is possible to draw edges between different clauses only. Okay, also it is not possible to connect a variable with its negation. This is very important. A variable with its negation connection is not possible. For example, if you consider this case, okay, this case, this is x1, this is x1 complement. Is it possible to connect these two? No. x1, this is x1 in the close 1, this is x1 complement in the close 2, but it is not possible. Okay. Okay, that is the next rule. Based on this rule, okay, there are two rules basically. Based on this rule, I will try to add edges. Okay, I will try to add edges. So, just explaining. Okay, for example, from here, you can note here x1. From x1, I can't add an edge to this. Why? Because basically this one belongs to the close. Okay, I'll just draw it. This is close 2 and this is close 1. Okay, I can't add x1 to x2. This is not possible. Why? Because it is not possible to connect two variables within the same clause. Okay, fine. Next, what I will do, I will try to add this clause from here. So only edges between the clauses is possible. Okay, this one and this one. Now I will try to add x1 to x2. Is it possible? So x1 to x1 complement. Is it possible? No. Why? Because x1, it is its negation. Okay, x1 to x2 is possible. Yes. Okay, so I will add x1 to x2. Okay, now x1 to this one is possible. x1 to x1 in this, yes, it is possible. This is close 3. Okay, this is close 3 and x1, there is an x1 here, also x1, it is possible. Okay, similarly I will try to add this one, x1 to x3, it is possible. In this way, based on this, I will try to add edges. Okay, okay, you just try to do it and you can understand how these connections appear. Okay. Okay. So then you can note that there are different edges. Then after adding all the edges, you will get a graph like this. Okay, you will get a graph like this. Okay, so now what I want to do is that I want to find a clique of size 3. Okay, now this is a graph corresponding to our CNF satisfiability problem. And now what I am trying to do is that the CNF satisfiability problem consists of 3 clauses. Okay, you can note here I marked. Here k is equal to 3. Okay, so what I will try to do is that here I will try to find a clique of size 3. Okay, is it possible? Yes, you can note here in this graph there exist different cliques of size 3. One of the clique is this one. This is one example. Okay, this is a subgraph which is completely connected. So this is a clique of size 3, and here you can note in this case x1 complement. Okay, there are 3 nodes. One is x2, another is x1 complement, another is x3. Okay, so what we will do is that we will take x3 equal to 1, x2 equal to 1, then x1 complement also equal to 1. Okay, x1 complement equal to 1. Then what will be x1? X1 will become 0. Other two are 1. So for this combination, we can check if x1 equal to 0, x2 equal to 1, x3 equal to 1 is applied on f. F is our equation. If we applied these values on this equation, it evaluates to true. Okay, so that means, okay, try to understand that concept. Okay, so that means what it means. It means this clique problem, this problem is basically a solution of our CNF satisfiability problem. Okay, so this is this and these are two equal. These are equal solution. So this clique is a solution to the CNF satisfiability problem. Okay, so using that clique we can find a solution to our CNF satisfiability problem. So that means that CNF satisfiability problem is reducible to the clique problem. CNF satisfiability is already proved it is NP hard. Then what about the clique problem? The clique problem also will be NP hard. Okay, that is, it is possible. It is possible to reduce the CNF satisfiability problem to the clique problem. So clique problem is also NP hard. So this is about this problem. Okay, so this is about proving a clique problem is satisfiable. Clique problem is NP hard. Okay, so now we proved clique problem is NP hard. Then my question is whether the clique problem is NP complete. What is NP complete means? It should be NP hard. Then additionally, the problem, the algorithm we use to solve the clique problem should be NP. Then we can say that clique problem is NP complete. Okay. Okay, this is about this session, and we completed this section. Okay, only this much questions you can expect in the university exam from this module, from this part 2. Okay, So tomorrow we will discuss part 1, module 6, part 1, branch and bound algorithm. Okay, that's the last topic. Okay, thank you. Please give your attendance. 1 minute. Please give your attendance in the chat box. Akash, Abhinand, Abhinav, Advaid, Adarsh. Okay. Adarsh absent. Ajmal, Akil, Sipol. Okay, Adarsh. Anaka, Anjali, Anugraha, okay. Atul, Atin, okay. Devika, Dilna, Jasna, Masna, oh, Jasna, okay. Karthik, Kirtana, Masna, absent. Neha, Nitin Babu, Nafaike, Muhammad Sinan, 1 minute, Muhammad Sinan, okay. Reza, Khalid, Rasana, Nehala, Rasa, Nehala, okay. Roshan, Pranavsi, okay. Roshan, okay. Risin, Sahlabi, Risin present, okay. Sahlabi, Sahlayan, okay. Then Salan, okay. Okay. Next, Sangeeta Saranga Sharana Shraddha. Sangeeta Saranga Sharana Shraddha. Sharun absent. Vishnu Vinod Vaishnavi Baby Sishma Anjali. Anjali. Okay. Sharun, okay. Okay. Thank you.